बिस्मिल्लाहिर्रहमानिर्रहीम। अल्लाहुम्मा सल्लि अला मुहम्मदिन व अला आलि मुहम्मदिन व बारिक वसल्लिम। रब्बिश रह ली सदरी व यस्सिर ली अमरी वहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली। Assalamu alaikum. I am Dr. Umar Farooq. In the previous lecture, that is lecture number 1, we studied about the reversible and irreversible reactions, forward and reverse reactions, dynamic equilibrium state, macroscopic characteristics of forward and reverse reactions, and macroscopic characteristics of dynamic equilibrium state. Today's lecture is Law of Mass Action, put forward in 1869 by Norwegian chemists Guldberg and Waj. So this law deals with the rate or speed of a reaction. By rate of a reaction or speed of a reaction, we determine how many number of reactant molecules are being converted into products per unit time. Note that in a reversible reaction, every species is a reactant and every species is a product too. I repeat, in a reversible reaction, every species is a reactant and every species is a product. Look at this general reversible reaction. Here A and B react to form products C and D. And this is to be noted that reactants of forward reaction, that is A and B, are the products of reverse reaction. Similarly, reactants of reverse reaction, that is C and D, are the products of forward reaction. मतलब forward reaction के जो reactants हैं, reverse reaction में वो products होंगे. इसी तरह reverse reaction के जो reactants हैं, वो forward reaction के products होंगे. I hope you understand. So the law states that the rate at which a substance reacts is directly proportional to its active mass, and the rate of chemical reaction is directly proportional to the product of the active masses of reacting substances. I'm gonna erase it and rewrite by highlighting some of the words, and that is active mass. Remember students, during a reversible reaction, the whole mass of a substance present in the reaction mixture does not participate in the reaction. Active mass of a substance is its mass that is being converted into product, or the amount that is actually reacting. Active mass is expressed as molar concentration, which is the number of moles of a substance per dm cube of the mixture, that is mole per dm cube. The active mass or molar concentration of a species is represented by square brackets. Consider a general reversible reaction in which A and B react to form C and D. If we write A in square brackets, it represents active mass or molar concentration of A. Similarly, active masses of B, C and D are represented by writing them in square brackets. So students, look at the statement of the law carefully. You will notice that it has two parts. This is the first part, while the second part is written in yellow. For the time being, I erase the second part and focus on the first part only, which states that the rate at which a substance reacts is directly proportional to its active mass. Note that this part of the law deals with only one substance. Any substance anywhere, either on left hand side or on the right hand side. As I have told you that every species is a reactant. Here, a substance may be any one of A, B, C or D. So I am gonna apply this part of the law on each substance and write it mathematically as follows. The rate at which A reacts is directly proportional to the molar concentration or active mass of A. यानी A के रिएक्ट करने की स्पीड या रफ्तार उसके अपने एक्टिव मास या मोलर कॉन्सेंट्रेशन पर मुनहसिर है. जितनी ज़्यादा मिक़दार होगी उतनी ही तेजी से ए रिएक्ट करेगा। ए के रिएक्ट करने की रफ्तार किसी और पर डिपेंडेंट नहीं है। इसी तरह the rate at which B reacts is directly proportional to its active mass. The rate at which C reacts is directly proportional to the active mass of C. Similarly, the rate at which D reacts is directly proportional to the active mass of D. I hope you understand. Now I delete the first part of the law and ask you to focus on its second part, which is the rate of chemical reaction is directly proportional to the product of the active masses of reacting substances. Let's apply the law of mass action on this reversible reaction, which actually comprises of two reactions, forward and reverse. Hence, we'll apply the law on both reactions separately by replacing the words of chemical reaction and reacting substances accordingly. So, for forward reaction we write, the rate of forward reaction is directly proportional to the product of the active masses of A and B, as A and B are the reacting substances of forward reaction. Mathematically, the square brackets represent active masses. Now, sign of proportionality changes to sign of equality if we multiply a right-hand side by a constant. In this case, it is Kf. So we get Rf equals Kf times the product of active masses of A and B. Let this is equation number 1, where Rf denotes the rate of forward reaction and Kf is called the specific rate constant of forward reaction. Now focus on the law again. For reverse reaction we write, the rate of reverse reaction is directly proportional to the product of the active masses of C and D, as C and D are the reactants or the reacting substances of reverse reaction. Mathematically, we write it like this. Again, square brackets represent active masses of C and D. To convert it into an equation, we multiply right hand side by a constant Kr. So we get Rr equals Kr times the active masses of C and D. So this is equation number 2, where Kr is called the specific rate constant of reverse reaction. So by applying law of mass action, we obtain these two equations. Let's rewrite the equation by including Kf and Kr in it. You know that at equilibrium state, rate of forward reaction is equal to the rate of reverse reaction. So, substituting the values of Rf and Rr from equation 1 and 2, we get this. Now, shifting the variables on the right hand side and constants on the left hand side, we get this expression. Since constant divided by constant gives another constant, so we let this third constant as Kc. Therefore, the above expression becomes this, where Kc is called the equilibrium constant and the above expression is called the equilibrium constant expression, in which the active masses of products are written in the numerator, whereas the active masses of reactants in the denominator. This is to be noted that for equilibrium constant we use capital K, but for rate constants we use lowercase k. Do not confuse them. Let us now derive expression for Kc for a general reversible reaction. as this is a partially general reaction because we have specified 1 mole of each substance. So when you specify something, it is not the general case. To make it a general reaction, we use coefficients A, B, C and D, where lowercase a, b, c and d are used to balance the equation, and they represent the number of moles of species A, B, C and D respectively. Now, according to law of mass action, rate of forward reaction is directly proportional to the product of molar concentration of A raised to the power of its coefficient and molar concentration of B raised to the power of its coefficient according to the balanced chemical equation. Using constant of proportionality, we get this. This is equation number 1, where small kf is the rate constant for forward reaction, and we write it on the upper arrow in the equation. Similarly, rate of reverse reaction is directly proportional to the product of active mass of C raised to the power of its coefficient and active mass of D raised to the power of its coefficient. Multiplying by constant Kr, we get equation number 2, where Kr is the rate constant for reverse reaction, and we write it with the lower arrow in the equation. So we get these two equations. As you know, students, that at equilibrium state, rate of forward reaction is equal to the rate of reverse reaction. So by putting the values of Rf and Rr from equation number 1 and 2, we have this equation. Again, transposing the constant terms on the left hand side and variables on the right hand side, we get this expression. But Kf over Kr is equal to Kc. So the above expression becomes this, which is the required expression for Kc for a general reversible reaction. So students, note that the coefficients in the equation of each substance appear as their respective exponents or powers in the expression of Kc. Let us now define Kc in a comprehensive manner. You see, Kc is the ratio of product of molar concentration of products raised to power of coefficients to the product of molar concentration of reactants raised to power of coefficients. Another way of defining Kc, which is not given in your textbook, is that Kc is the ratio of forward rate constant Kf to the reverse rate constant Kr. At the end, let's talk about units of Kc. Units of Kc vary from reaction to reaction. That is, different reactions have different units of Kc. To find the units of Kc, we have to write the balanced chemical equation first, and then expression of Kc from it. Then in the expression of Kc, write mole per dm cube in place of each substance. Finally, use laws of exponents to obtain the units of Kc. Note that if the number of moles of reactants are equal to the number of moles of products, then there is no unit of Kc for such a reaction. There is a shortcut method as well. Find the difference of number of moles of products and number of moles of reactants and raise this difference as a power of mole per dm cube. Simplify to get the units of Kc. Let me now explain these points with the help of a few examples. Hydrogen and iodine react to form hydrogen iodide. First, we balance it just multiplying Hi on right hand side by 2. Then write the expression of Kc for this reaction. concentration of HI in the numerator and those of H2 and I2 in the denominator, raised to power of their coefficients. Then in place of active mass we write its unit, mole per dm cube, simplifying to get mole per dm cube raised to power 0, which means 1. That is no units. Why? As there are equal number of moles of reactants and products. Look at this reaction between nitrogen and hydrogen gases to produce ammonia gas. First we balance it. इस मकसद के लिए जहां 2 हाइड्रोजन एटम्स हैं वहां 3 से, और जहां 3 एटम्स हैं वहां 2 से मल्टीप्लाई कीजिए, नाइट्रोजन खुद ब खुद बैलेंस हो जाएगी. After balancing we write expression of Kc, of course with ammonia in the numerator and nitrogen and hydrogen in the denominator. In terms of mole per dm cube, simplifying using laws of exponents, 2 minus 1 minus 3, to get mole per dm cube raised to the power minus 2. Further simplifying we get mole raised to the power minus 2, dm raised to the power 6. Let us apply shortcut method to check your answer. Number of moles of reactants is 4 and number of moles of products is 2. So their difference is minus 2. So raising minus 2 to the power of mole per dm cube, we get the units of Kc. Next we have reaction between sulfur dioxide and oxygen gases to produce sulfur trioxide. To balance it, multiply both SO3 and SO2 by 2 and then writing the expression for Kc in terms of mole per dm cube, simplifying to get mole per dm cube raised to the power minus 1. Finally, the unit of Kc is mole raised to the power minus 1 dm cube. Let's apply shortcut method just to check our result. We have 2 mole of SO2, 1 mole of O2, so total moles of reactants is 3 and 2 moles of product. Let's find their difference. 2 minus 3 is minus 1. So mole per dm cube raised to the power minus 1, which satisfies our result. But remember students, in exams you will find unit of Kc from its expression. Shortcut method is just to check your result. I hope you understand. If you have any questions, please do write in the comments below. Thank you.